Welcome to EPG Pathshala. We are looking at computer science and we are looking at computer networks in this series. So, as far as computer networks is concerned, we have been taking a top down approach. So, we have been looking at layers starting from the application layer and we are almost at the end of the TCP. So, we will kind of do a wrap up on whatever we have left over with respect to TCP. So, we have covered sufficient ground in TCP. So, there are some other things that we still have to be aware of when it comes to understanding TCP. So, those are things that we will cover in today's lecture. So, we will start off with TCP and congestion avoidance. We have looked at the congestion control mechanisms of TCP in detail. So, we will look at how congestion avoidance is added to TCP. Second thing we will look at is as part of that we will look at random early detection and we will look at the ECN techniques. Then we will also be looking at various options that are available in TCP and then we will look at different timers and how timers are managed in TCP and then of course we will try to conclude with an introduction to socket programming. So, if you look at the TCP's congestion performance, so we see that basically what TCP tries to do is a guessing game. So, it assumes that whenever a packet is lost, it must be because of congestion, it just guesses it must be because of congestion and tries to do some congestion control mechanism by reducing the window size and reducing the amount of data that it is sending into the network. So, the question here is if it were to get some more help from the network, would it be able to do better? So, if the routers could inform the end systems about congestion, would they be able to do better? So, that is what we are trying to understand. If we could do that, definitely our congestion performance could be improved. So, how can this notification be given? Either it has to be an explicit notification which comes from the router or it has to be some kind of an implicit notification. So, there are both these mechanisms can actually be used. So, what is it that can be done in the TCP IP context? So, that is what we will first look at. Now, to understand this, so let us just take a look at what actually happens at the routers. So, if you look at what we have at the routers, basically there are some buffers, right, and both at the input and the output there are buffers and packets they come into the buffers, they are queued at the buffers and then spaces are allocated to the buffers and then they get scheduled for being sent out on the different output ports through the output devices. Now, if there is some QoS, then there is some traffic control also that takes place, but even without QoS, simple IP forwarding, it goes into the output queuing and it is sent out. So, there are different queuing disciplines and depending on the different queuing disciplines, if you are doing some quality of service kind of mechanisms, then depending on the queuing disciplines, you would have different quality of services being implemented. Okay? So, that is one part of it. But even if you are not doing QoS, as I said, simple output queuing is what is normally done. So, now what happens actually when you do this, when we have these queues? The typical approach that is followed for resource allocation is that we use a simple first in first out queue and what is called as a drop tail approach when it comes to handling packets when they exceed the size of the queue. So, that is you keep transmitting packets in the order in which they arrive and when there is no buffer space, so you at the tail of the queue, whatever is there at the tail of the queue, that is dropped. So, the queue is full, then we drop the incoming packet. So, this is a very simple mechanism that is normally used in most of the routers. So, in this situation, let us look at what actually happens when we have this kind of situation. So, now we know that TCP depends on packet loss, right. This is how the normal TCP's congestion control mechanism works. So, let us look at what TCP does in this kind of a drop tail queuing mechanism. Now, we said that TCP depends on packet loss. So, whenever there is a packet loss, it takes it to be an indication of congestion and immediately what TCP will do is, it will drive the network into a packet loss situation by continuing, okay, normally what TCP will do is, it will continue to increase the sending rate and therefore, until it gets the feedback that a packet has actually been lost, it will keep sending data into the network and remember that it is normally increasing the amount of data that is sending into the network until it receives the feedback. So, until the feedback is received, what is actually happening is that more and more packets are coming into the network, which obviously is also increasing the number of packets that are lost, because if you are using drop tail queuing, the extra packets that are coming in are going to be dropped, right. So, this is something which happens. So, you will find that a number of packets are coming in, right, which are coming, all those packets that are coming in when the queue is full will all be dropped. So, which means it will lead to what we call as a bursty loss, as a burst of packets which are all going to be dropped. So, when a link is actually becoming congested, you find that more and more packets are actually coming into the queue and all of them are being dropped. So, then finally what will happen, you will find that number of packets will be dropped. Because number of packets are dropped, then TCP's congestion control mechanism will come into action and then only the number of sending rate will be decreased. Okay. So, this bursty loss is a major problem that we have with this drop tail queuing approach. Okay. So can we do better than this? So that's the question that we want. Okay. So this slow feedback that we have from drop tail queuing, right? So this is basically what we are trying to address. So but we know, see the problem here basically is that the feedback actually comes to you only when the buffer is completely full. Though we actually know that the buffer has started becoming full for quite a while. That is, if you are looking at if suppose the router were to look at the queue lengths, it will actually identify that the buffers are becoming fuller and fuller, and which means that congestion is beginning to set in. Okay. So can this behavior of the buffers becoming full, okay, can this be tracked and can this be informed to TCP? So that is what we would like to do. Okay. So in this case, when this buffer is getting filled, okay, so what is happening is that the RTT will increase, and because of the increase in the RTT, there will also be a variance in the RTT. Remember, because more and more packets are in the queue, so obviously the delays will be higher. Okay. So now the question is, can we give earlier feedback? Okay. Now to give earlier feedback, there are again better things that we could do when you are giving this earlier feedback. So when we are giving an earlier feedback, we can just pick 2 or 3 flows and slow them down rather than slowing down all the flows. Okay. So we can get them to slow down also before it is too late. That is, even as you see that the queues are becoming full, let us do something about indicating to TCP that congestion is likely to take place or beginning to take place, and ask TCP to slow down at the rate at which it is sending data. Okay. So this is what we try to do in what is called as random early detection or the RED mechanism. So RED is a mechanism that is used along with other routers, okay, in order to inform TCP in some manner that the buffers at the routers are becoming full. Okay. So how does the router inform the end system, the host, or the TCP which is running at the host system? Now there is no direct mechanism to inform that. So what the router will do when it is running the RED mechanism is that it will randomly drop packets. Now remember that a packet dropped is a signal of congestion for TCP. So what happens in a RED based approach is that the moment the router notices that the queue is getting backlogged, okay, it is getting fuller and fuller, then it just randomly drops packets. So the moment it randomly drops packets, okay, that becomes an indication of congestion to TCP, and TCP now will start reducing the amount of data that it is sending into the network. That is based on TCP's normal congestion control mechanism, because the moment it does not get the acknowledgement, a packet is dropped, it will automatically decrease the congestion window size. Okay, so this is what we do. So now, but how do we said we will randomly drop packets. Now if you are randomly going to drop packets, then obviously we need to have some kind of a drop probability that we will need to calculate. So how do I base this probability on? So normally what is done is we base it on the length of the queue. So what we say is, if you keep monitoring the queue length, if the buffer is below some level, if the length of the queue is below some level, do not drop anything, things are going fine, right, just let them go. But the moment it crosses some threshold, so then as a function of the queue length, we will start dropping packets. Okay, so this is the idea that is used in random early detection. So let us look at the details of how exactly this is done. Okay. So what is done is, we said that we are using the queue length as an indication. So what we do is, we first calculate the average queue length. So the average queue length is calculated as a weighted running average, similar to what we have seen in TCP's timeout calculation, right. So we have seen that you take the sample RTT and the existing RTT value and you calculate a timeout. In the case of timeout computation, we have seen how that is done. A similar weighted averaging mechanism is used here. Only thing is, now we are averaging the length of the queue. Okay. So what we take is the sample length, that is the current length of the queue, and what was the previous average length of the queue. So you weight this by a factor of weight. So this is weighted by a factor of 1 minus weight. So obviously weight is between 0 and 1, okay, and you calculate the average length. So this is the first thing that is done. So we keep calculating average lengths. So in a software based implementation, typically the queue length is calculated, this average length will be calculated every time that a new packet arrives at the gateway or at the router. In hardware, you could actually calculate it at some fixed sampling interval. So you could say, for instance, at every so much interval, I will keep calculating the average length, and I determine what the average length of the queue is. Okay. So once we have this average length, so what we now do is, now remember, now we use 2 thresholds, one called the minimum threshold and the maximum threshold. Now the minimum threshold is an indication for us basically that things are okay. Okay, so starting from here, so let's say my minimum threshold here is here. So as long as I have packets which are less than the minimum threshold, that is the average length is less than the minimum threshold, then you just keep queuing the packets. We are not dropping any packets. The packets get queued. But once the threshold, the average length is between the minimum threshold and the maximum threshold, that is it is in this region. If it is in this region between the minimum threshold and maximum threshold, then it indicates that the queue is getting fuller. So now we calculate a probability value, and you drop the arriving packet with probability P. So we do not drop all packets, but with some probability P we will drop packets, and this dropping probability will obviously increase as the length of the queue increases. So you need to have a probability calculation mechanism which ensures that. Okay. Once it crosses the maximum threshold, the average length crosses the maximum threshold, then you will definitely drop the arriving packet. Okay. This is basically how the red mechanism works. Okay. So how do we calculate this drop probability? That is the next part. Okay. So as you can see, this is basically how the drop probability function should look like. So what we are showing here is on the x-axis you have the average length, on the y-axis we have the dropping probability. So now as long as the length of the queue is less than the minimum threshold, we are not dropping anything, right? So the probability is 0. We do not drop any packets. Now between minimum threshold and maximum threshold, the probability, the drop probability will increase. Okay, we would like it to increase linearly, and once it crosses some maximum threshold, right, we will definitely drop the packets, which means drop probability becomes 1. Okay, so this is what is shown by this figure. So between this min threshold and max threshold, how do we actually calculate the probability value? So that is what we are looking at. So what we do for this purpose is that we use a factor called max P. Max P is some value which is between 0 and 1 obviously. This is the maximum value to which you allow the drop probability to grow. Okay. So you calculate your a value called temp P as a function of the of max P and of the average length and the minimum threshold and the maximum threshold. So basically we look at it like this. So it is calculated as average length minus minimum threshold, whatever is the current length minus minimum threshold, divided by max threshold minus minimum threshold. That is how much of this in this interval, how much of this interval is actually currently being filled up by the queue. Okay, so that is what we are looking at. This is multiplied by max P, okay, and we call this as a factor temp P. Now the drop probability is calculated as temp P divided by 1 minus count into temp P. Now this count here is the number of packets which are queued since the last drop. Now it is interesting to note why we have this count value over here. See, basically what we would like to do is, if a packet has just been dropped, we do not want to drop packets immediately after that. We would like to space out the dropping of the packets. Okay? But if your drop probability was only dependent on the average length and the minimum threshold, maximum threshold, it is possible that you will get a higher value of drops that take place, and these drops would take place close to each other. So we want to space out the drops. So to space out the drops, what we are doing is we are including a factor which says number of packets which are queued since the last drop. Okay. So once you do this, you can see what happens with respect to this formula here. Now when your count value increases, that is, which means I have not dropped packets for a long time, so naturally count into temp P will increase. So which means 1 minus count into temp P will decrease. If this decreases, then your P, the drop probability, is temp divided by a smaller factor, so this will increase. So when the count increases, you will find that the drop probability increases. When the count is less, that is, if I have just dropped a packet, immediately after that if you look at, this count value will be small. So 1 minus count into temp will be a larger value. So you are dividing by a larger value, so the probability, drop probability will be a little higher, will be a little lower. Okay. So this is basically how you are calculating the drop probability. Okay. So the suggested values for these parameters that we have looked at, right? We need, if you set the parameters appropriately, we can get the desired behavior. So by doing a number of experiments, people have come up with different values that are used for these various parameters. Okay. So the suggested value for WQ, right, that is where somewhere between 0.001 to 0.0042, and the minimum threshold and the maximum threshold, they normally depend on the desired average size queue. Okay. So if you are having a bursty traffic, then it makes sense to increase the minimum threshold to maintain the link utilization, because you are expecting many packets to come at a time. Okay. And maximum threshold will depend on the maximum average delay that is allowed, which means if my threshold is larger, that means packets can get queued for a longer period of time, and so by the time I get feedback to TCP, it will take a longer time. So if you can tolerate delays which are larger, then we would go in for then use a larger value of max threshold. Okay. So min threshold and max threshold are fixed based on these parameters. Normally red is considered to be very effective, when this difference between max threshold and min threshold is larger than the typical increase in the calculated average queue size in one round trip time. That is, in one round trip time, whatever increase I expect, my max thresh minus min thresh should be greater than that. So then red turns out to be pretty effective. Okay. So the rule of thumb normally that is used is that the maximum threshold is treated to be about 3 times the min threshold. That is the kind of things that people have been using. Okay. Red, by the way, was invented by Floyd and Jacobson in the early 1990s, and they came up with some guidelines for these things. Okay. So the next factor that we have to look at is that max P that we have. Remember that we have a factor here called max P that we are using. Okay. So how do we set this max P factor? So max P is again based on a lot of experiments. It has been found that in order for the network to be stable, okay, there is a stability argument which says that we do not want frequent oscillations. That is, we should not have a situation where TCP will go into congestion control mode very quickly and immediately comes out of congestion, and again it has to go into congestion. We do not want to have such oscillations because of the feedback that you are giving. Okay. So we would like to have some kind of a stability. So the stability argument is that red with a smaller max P will reduce the oscillations, okay, in the average, and therefore you will have a better marking probability. Okay. So max P is normally recommended to be less than 0.1. So that is basically how these things are set. Okay. So this is just an example of red in operation. So you can look at this example here. Let us assume that we have 5 packets which are coming in. Okay. We have a queue here. Assume that the minimum threshold is 1 and the maximum threshold is 4. And max P is 0.1, and taking a W value of 1. So what W equal to 1 indicates is that the average queue size is equal to the present queue length. Okay. So that is what we are looking at. Right. So if you look at this, let us say initially when packets are coming in, you can see that the temp P value will be 0, P is equal to 0 because the average length is 0, right. So this is what you have. So no packets are dropped. So initially packets start getting queued. So let us say 2 packets are there in the queue. So now the average queue length is 2. So your temp P is calculated as 0.1 into average minus minimum threshold 2 minus 1 divided by maximum threshold minus minimum threshold 4 minus 1, right. So which comes to about 0.033, and we have not dropped any packets so far. So our count value is 2. So our probability value will be calculated as 0.033 divided by 1 minus 0.33 into 2 comes to about 0.035. Okay, that is the drop probability. So let us say based on this probability, one packet, the third packet is dropped. Okay. So now let us say some more packets come in, few more packets have come in, and the average queue size is 6. Okay. So let us look at what happens here, right. So the average queue size is 4, all right. So when the queue size is 4, because we know the maximum threshold is 4, right. So let us say 4 is the queue size. Now 2 more packets are coming in. So look at what happens in this case. So 4 minus 1 divided by 4 minus 1. So my average value is 4 and the maximum threshold value is also 4. So 4 minus 1 by 4 minus 1, that becomes 1. So temp P is equal to 0.1 into 4 minus 1 by 4 minus 1, which is 0.1, and your probability value is 0.1 divided by 1 minus 0.1 into the number of packets that we have not dropped, the count value. So let us say the count value is 5. So then your probability drop will be 0.2. You can see that compared to the previous value here, this probability drop has increased, right. Dropping probability has increased. So now it is possible that we may drop, if it is 0.2, almost 2 out of 10 packets will be dropped, right. So you would, maybe you will drop 2 more packets over here, okay, and then this information will go back to TCP. So this is basically how red will operate. Okay. So the properties of red, if you look at it quickly, okay, you can see that basically what it does is, it drops packets before the queue is full. So in the hope that you can reduce the rates of some flows, okay, and it drops packet in proportion to each flow state. So there are more packets coming in on a particular flow, you would like to drop more, higher chance that that flow will be selected for dropping packets, okay, and the drops are spaced out in time, so that you would like to have desynchronize the TCP senders, okay, and you can tolerate burstiness in the traffic, okay, by basing the decisions on the average queue length. So these are the basic properties that we have of red, okay. But the problem with red is that it is difficult to tune these parameters correctly. That is, how early to start dropping packets, what should be the slope for increasing drop probability, what time scale should be used for averaging the queue length. So all these are actually tunable parameters, but it is very difficult to set them right because there is a lot of change in the actual traffic that comes into the network, okay. So red is implemented in practice, but it's very difficult to get this tuning right. Okay. So in fact, there are many variations of red. So we have something called blue, we have something called F red, and so on. So there are other variants of red that are used. But to solve this problem further, okay, there's another method which is used where we make use of explicit congestion notification. Okay. So this is also another technique which is supported in routers, and there is also support in with respect to TCP and IP in order to do this. So what we are saying in explicit congestion notification is that it is good to give early feedback, okay, but it is bad that you have to drop a packet to give the feedback. So instead of dropping a packet, if I could just mark some bit or something in a packet and send that as the information to the router, to the end systems, to the host, they could use that information instead of dropping a packet. Okay. So this is what we do in explicit congestion notification. So the router actually marks a packet with an ECN bit, and the sending host will interpret that as a sign of congestion. Okay. So where do I put this ECN bit? So that comes the next challenge. So what we normally do here is that we make use of 2 bits in the IP header. So remember that in the IP header we have these type of service bits in IP version 4 which are really not fully used. So we take 2 bits out of that and use one to indicate the ECN mark and 1 bit to indicate that the host, systems are capable of supporting ECN. So using these 2 bits, an explicit congestion notification can actually be given by the router to the end host, and using this congestion control can be done in a better manner. In fact, congestion avoidance can be done in a better manner. Okay. So that's about the congestion avoidance support for TCP. Okay. So next thing we will look at is the different options that are available in TCP. So remember, if you look at the TCP header, you will find that there is something called TCP options over there. So what are the options typically that are supported by TCP? So these are some of the important options list that we have. These are the values that the options field can take. There is something called an end of option list, which says that the kind basically indicates the type of the option. So kind equal to 0, and if the no operation kind is equal to 1. So these are pretty much straightforward. And there is something called a maximum segment size option that we have. That is, the two end systems can actually negotiate on the maximum transfer size that they want to use, the actual MSS that they would like to use. Okay. So this is normally done at the 3-way handshake time. So this is a parameter that can be negotiated between the two ends, and we have an option for doing that. These 2 other options, window scale factor and timestamp, okay, they are used for better purposes. They are used to improve the performance of the TCP protocol as such. Okay. So if you look at this window scale factor, okay, this window scale factor actually has been proposed to address one particular issue. The issue is that when the window is too small, especially in gigabit networks, okay, because you only have about 16 bits to specify the window size, which means only about 64 kilobyte can be the window size, and 64 kilobyte window size can easily get exhausted in a gigabit network. So the amount of throughput that you can support is limited by this window size. So can we increase the window size? So how do we increase the window size? Because only 16 bits that are available. You can't add more bits in the header asset. So what we do is we negotiate a shifting factor as a window scale factor option. Okay. So the shifting factor basically says you give me some value, but I will scale that factor up by some count value. So which means you may say that the window size is 100, but I will use a scaling factor of 16, which means I will say actually the window size is 16 into 100, which is 1600. So that way my 64 kilobyte limit that I have can be expanded because I can multiply it by a scaling factor. So the moment I multiply it by scaling factor, I am able to support larger window sizes. So this is what is supported with the help of this particular option. So the window scale factor, if you look at, you specify basically what is the shift count. So if you specify a shift count of 14 bits, it means that you are multiplying the value that is given in your window size, which can go up to 2 power 16, can be multiplied up to a value of 2 to the power of 14. So you specify the shifts in powers of in a binary value, and the actual multiplication factors are in terms of powers of 2. So you multiply that and you can get a larger window size. So this is one very important option that is currently used. The second option that we have is with respect to the timestamp. Okay. Now in order to improve the RTT measurement, so if you look at the round trip time, remember that all our calculations in TCP are all based on the round trip time. So we would like to have a very accurate calculation of this round trip time. So normally what happens is that we are using a very coarse grained timeout which is used for calculating the round trip time. So to improve that, what we do is we use this timestamp option. So as part of the timestamp option, what we are doing is we add some information. So what is the information that we add? That is, when the packet is sent to the receiver will note the time at which it receives the packet, and it will copy that and reply that value. It will send that value back, the timestamp value back in the packet. Okay. So, as part of the timestamp option, we have an option to specify what is the value, what is the timestamp at which I received the packet, and what is the timestamp at which I am sending the reply. Okay. So, the sender now can update the RTT when it actually sees this timestamp value. So, this is one use of this timestamp option. Okay. Second place where this timestamp option is useful is also to protect against wrapped sequence numbers. Remember that our sequence numbers go from 0 to 2 to the power of 32 minus 1, and again on very high speed networks this number can be exhausted, so which means it will wrap around after 2 to the power 32 minus 1 and come back again to 0. So, you may have 2 packets with same sequence number, but they are actually of different rounds. So, this is something we need to differentiate. Okay. Here again this timestamp option helps. So, if I put the timestamp along with the packet, so I will look at the timestamp plus the sequence number. Now, this will help me to differentiate whether it is a packet which belongs to a previous round or the next round. Okay. So, you are avoiding old segments getting confused with the new segments. Okay. So, how do we enable these options? Again, all these are done when we do the three-way handshake. Okay. So, when the three-way handshake is done, all these parameters that these options will be used will be negotiated and they will be decided. Okay. That is about the options. Similarly, timer management is again another very important aspect of TCP. So, there is a retransmit timer, there is a persist timer to prevent deadlocks, keep alive timer and so on. So, if you look at the list of timers, so this is basically the list of timers that we have. There is something called a connection timer. Now, this is used whenever a new TCP connection is established. You wait for a timeout value until the connection, for a connection response to be received. If you do not receive within that time, the connection will be aborted. Okay. Similarly, it is a retransmission timer, we know this already, right, the time at which you will have to retransmit. So, delayed ACK timer. So, this is used when if the receiver would like to wait before sending out an ACK. If you want to use a delayed ACK option, then we have a delayed ACK timer for that. There is a persist timer, this is used for sending out periodic probes when the window closes, right, this is another timer that is used. So, then we have keep alive timers, again if the connection is idle for a few hours for instance. So, then we would like to use a keep alive timer which periodically sends out probes to say that look, I am alive, this connection is still alive. Okay. So, that is a keep alive timer. Similarly, there are timers which are used as part of the state diagram in the fin wait to state and in the time wait state. Okay. So, this is we have looked at these when we talked about the connection state diagram. So, these are the different lists of timers that are used. So, now any discussion on transport layer will not be complete without talking about sockets, which is the interface to the transport layer, to the network as such, right, from an application's perspective. So, from an application programmer's perspective, I need to know how I can make use of these services, right. So, we will spend a few minutes looking at what we mean by the socket interface, right. So, just as we have file descriptors and file interface to access files, we have something called a socket interface to access the network related functions. So, there are different types of sockets that have been designed, that can be defined in as part of the Linux kernel or as part of any of the kernels, and we have different APIs which are used for accessing these things. Okay. So, let us just take a look at what is normally done, okay, in terms of creating a socket. So, let us say we are doing a socket creation in C. The same thing could be done in Java or any of the other languages as such. So, normally you will see that you will define a socket with a domain, a type and a protocol. So, S is the socket descriptor, which is basically an integer, which will be like a file handle, it is a socket handle, and domain specifies which is the domain, the addressing family in which you are working. So, typically we are working with the internet family. So, IPv4 will be the value that is used there. There is a type which specifies what kind of socket we are using, what type of socket. We have a stream socket, we have a datagram socket. Now, you can easily understand what these two must be meant for. Stream socket is used for a reliable two-way connection based service, which is TCP. Datagram socket is used for UDP, unreliable connectionless service. Okay. Then there is a protocol field which tells us what kind of protocols are being used. So, there are again different options that are available for these things. The socket call basically will tell you that there is an interface through which you can access the network. Okay. It still does not tell you where the data will be coming from. Okay. So, to do that we need to understand how basically the socket functions are handled at both the client side and the server side. So, let us quickly look at what happens on the client side and server side for a TCP socket and similarly for a UDP socket. So, on the TCP side we all know that initially it will be the server that starts. So, the server will make a socket call, which means it obtains a descriptor, and it calls a function called a bind function. This bind function will assign an IP and a port to the socket, and it goes into the listen mode. Okay. Now, in the listen mode, it is basically doing a passive socket connection. So, it creates a connection queue and it is waiting for requests to come in from the other end. So, then it goes now on the client side, the client side will open a socket, make a connect. Now, this is an active connection that it is doing, right, it is an active open. So, it will establish a connection with this. Now, this accept is a blocking call, so it will be waiting until this connection is established. Once this connection is established, now this fellow can now write data and he can read the data, and this he can write the data and he can read data. So, this will go on until they decide to close the connection. So, when they decide to close the connection, both sides will do a close call and they close the connection. Okay, this is basically what will happen in a TCP socket. You can relate it to the TCP's connection state diagram and you will be able to understand what is happening. So, similarly, if you are looking at a UDP socket, you will find here that there is it is very simple, right, because there is no connection establishment. So, all you do is you open a socket, you bind it to a port, to an IP address and a port number, okay, and you are basically waiting to receive from the other side. So, you do a send to from here, you receive on this side. Now, this call will block until it gets something from the sender. Okay. So, this whole process will take place in a UDP socket. You can see that there are two simple mechanisms with respect to using these sockets. So, all we need to understand with respect to sockets is what is the socket interface and what are the different functions that are available and how you can use them to connect up different nodes using either UDP sockets or TCP sockets. Okay. So, with this we have kind of wrapped up on various aspects of TCP. So, in this particular session we have looked at congestion avoidance, we have looked at RED and ECN, we have looked at the different options that are there in TCP, we looked at the timers, and we have looked at using the socket API for TCP and UDP. Okay. Thank you.